Oh, okay.
Yeah.
Yes,
The other meeting.
So all this message. So it's the same team that was here, the same participants as yesterday?
Probably have half who we had yesterday.
Good job.
And I will.
All right, we will start the benchmarking meeting now. Maybe make your way over to this table. Looks like a little bit of a small team this time. Feel free to bring your lunch too as well. That's fine. And Pedro, can you hear us?
Yes, I do. Can you hear me?
We do hear you. So
Okay.
what we'll do is, I think we'll have a couple more people just getting a drink. Give us a minute here. Austin is going to join. Oh, you're coming, Austin. Are you joining too, Paul?
Yeah.
Feel free to get coffee.
I get my call.
Yeah, so we have one person online. I think everyone here might have been in this meeting yesterday, so, but why don't we just quickly go around and say our names? We'll be friendly, and so Stephen Miller, AVCC Technical Chair.
Isaias Pech, Salantis, AI.
Dave Myers with Streetscope.
Austin Pipely Bosch, Product Management, ADAS and Corporate Systems.
Rohit Naharia, Bosch for Advanced Engineering.
Jyotika Ajavne, RAS Architects, Synopsys.
Paul Zarati, Automotive System Architect with AMD.
Umair Hashim, Performance Analysis Lead at ARM.
Right, Pedro, go ahead.
This is Peter Djurjevic, Autonomous System Design Engineer from ARM.
Good. So for the schedule, maybe it's a little bit hard to read for everyone in the room. The first hour, we're gonna, I think I'll just do it till 2 p.m. So 45 minutes. We're gonna continue that discussion we were having on the system level benchmark. I think what I'll do is I want to look a little bit at what we would benchmark if we're also including the infotainment, the IVI piece as well, just to start, kind of expanding the system scope a little bit. And then the other hour from 2 to 3, Predrag will be leading that discussion, and that will be actually looking at some of the issues for foundation models in vehicles, right? So, obviously a very timely AI topic. What I will do now is change.
Somebody else joined on. Oh, great.
Yeah, Dongun, do you want to introduce yourself? Okay, okay. Well, we will, let me figure out the teams for a second. There. All right, hopefully everyone sees this reasonably well. Let me just remind me. So I think there was the spot where we ended up yesterday was the following, which was kind of talking a little bit about the steps to achieve a system level benchmark, SLB. That's what that means. I think for the time, since we already went through this and got some pieces, there was 3 other topic areas that I wanted to discuss relative to benchmarking. One is what I'm calling system software benchmarks. So OS hypervisor, what that could look like. Do we want to do that? The next one would be deployment benchmarks. So thinking a little bit here to what Sophie does with cloud native development and virtualization tools or containerization. And then the last one, and I stole this image from Austin's slide, But talking a bit about the domain fusion benchmarking. I think we have, roughly 45 minutes, so let's spend, we'll target 15 minutes per topic, actually. Why don't we do it that way? But maybe since we just saw Austin's talk, let's talk a little bit about what we would want to focus on if we were thinking of something like a domain fusion benchmarking. In terms of, so the first one I think is defining what the system workloads are. And certainly those of you that have more experience in the infotainment space, maybe let's, just gonna actually clean this up a little bit. What would be the system workloads?
So Austin, I'm just talking about this actually. So in terms of, again, my view, and I'm happy to change it, but what I was thinking was maybe we could define the different features that that make up L1, L2, L3. And they may even be like digital cockpit workloads. Look at it, just the modularity piece that Neil was maybe talking about, right? If we have modular features, right, we can implement those as benchmarks or unit tests or whatever you want to call it, right? And that can be your matrix to say, okay, for this feature, this is the performance requirements for it, right? If you run it on CPU or accelerated with GPU or any other accelerator, maybe DSP or whatever, we can then start to map out, here's the feature set, here's a reference implementation of it, and then this is how much compute it requires. And then you can pick and choose. You can go both ways, right? You can say, okay, here's my performance budget on my hardware. If your hardware is fixed, right? You say, okay, this is my budget. What features can I land within this performance budget? And then you start picking those features out, and then look at the compute demands, requirements, and then you compose, all those features you want to deploy on it. Equally, you can say, if I want to integrate these features, what would it take? What kind of compute would it take? And then you design a system around it.
Yeah, it's kind of what we were talking about yesterday. Saying, let's not maybe get away from level 1. I think this is Paul's point. Level 2+, and just define, okay, give me some representative sensor sets and I guess feature sets. We can do that. Maybe what we'll do first though is just on maybe the domain fusion HMI infotainment piece of it. Whether we want to call it features or maybe I'll just change the wording here. First of all, what are the things we think would be important to benchmark for this kind of system? Then maybe we'll jump to the feature benchmark. Maybe we'll give a first rough pass at what a level 1, level 2+, and a level 4 system would have or something. I don't know.
One question. So when we say domain fusion benchmarking, this is only read from the ADAS perspective, or
No, it would be the whole
everything,
the whole
okay.
SoC.
The whole SoC.
Yeah.
So like GPU rendering.
Right. Then so that would be, I guess, the visualization.
Yeah, visualization.
DSP, their audio and data.
Or is DSP.
Real time.
Yeah, that was all my thinking, real time and what you can know.
So visualization slash audio. And so under visualization, that's where you're gonna include all of the display drive, and then that'll get to your point about what level of the car is it? How many displays?
And the display drive is also the resolution of each display.
Yeah.
Frequency.
Well, and like Austin, even vision processing necessary.
You mean ISP or you mean AI?
Well, it's interfacing to a camera, potentially ISPing it, potentially doing a graphic overlay.
For OMS, right? An OMS camera with RGB IR.
Like prevented
Yeah, so you could be pulling in an image.
Okay.
And then it's overlaying.
If you look close to the bus, these have a car with a front camera for navigation, so you get the navigation route here, it's on the road. So with the camera video screen, you have these arrows on the inputs.
Augmented
So
reality
then,
camera.
Yeah.
Is there extra load for the heads up display, or is that just a display?
Yeah, the warping. So when you have the display, then you gotta warp the image and that typically uses GPU.
For the heads up.
For the heads-up display.
And the heads-up display comes outside. And we, as a unit, would be sending the information to data, but the actual.
It depends.
It depends
It
on how
depends. Some
rich-
of them are smart huts where then it's a standalone module, gets Ethernet or CAN, and some of them are more of a slave type.
But in
display.
that case, it's already a display. It's technically like a display you're sending, it's a display you're sending. One kind of.
It depends how rich the content on the hub is, right?
Yeah, and once it is rich, it's equal to a display, though you are not showing as a display. So if you count that in the GP, you might be already counting that. And then you.
But some displays are just you're just gonna project whatever movie or something, right? You're not typically
Yeah.
using the GPU to do additional computation.
But for the HUD, especially for the Fusion SoC, it makes sense to have a slave type HUD and then do all the pre-processing, including warping in the HPC, and then send it as a dummy display.
Yeah, I mean, here, let's just try to get a complete list. It doesn't have to be.
No,
The AI course, the video perception, is that in L2 we are considering that, or should we keep it separate? Because L2 means functional.
Yeah, maybe, but I'll do, yeah, I can do maybe separate.
Perception can be in camera, in cabin camera or outside.
Yeah, we did add separately the occupant monitoring system, just because it's often, sort of, let's say, developed differently. Then for the, I guess the sensor set for perception could be,
and another topic, what we said about real time and what you can do on the Android or some of
The
the.
workload on the
Part of-
CPU, but also the real time codes. Are we utilizing it?
Course.
and there's also like, yeah, I guess hard task. And then you meant for the real time core, you meant the safety island or? Is there a heavy like interface for off boards? This,
Like sending it somewhere on the cloud?
yeah, I mean, I don't know,
Encoder,
let's
decoder.
say streaming video.
Oh, yeah, that's right. Encoder, yeah.
Encoded, decoded the video. We use.
I mean, that's often usually there's an embedded core for that, right? Or hardware.
Yeah.
So it's more, but it's a data flow then.
Yes, it also is relevant because you get the video stream from a camera over Ethernet for whatever reason, like that also comes to the same channel. The movies from download also use the same thing for Netflix. Yeah, the DRMs which is running on that. It wouldn't impact on anything, but maybe there is impact, like who knows, like two things in parallel.
And then I guess if there was anything, yeah, I'm just trying to think for the cloud connectivity. So if it's video, it would be heavier. If it's voice or is that pretty? Again, I mean, part of the reason we can, obviously we can list all the workloads and then start deciding
Yeah.
which ones
Yeah, right.
it's not so much worth doing. So
I mean, the video encoder decoder is actually quite, I think it's low hanging fruit because there are standard frameworks and plugins that you get for like streamer, FFmpeg or GStreamer, and then it's up to the codec provider to provide the plugin for it. And it's very easy.
Unless you have a hardened version, then you could be limited whether you're 2.6. Under the audio, like, what's the subheadings of that? You know, I mean, there's audio processing for the sound system in the car. I mean, you could start to get into noise cancellation and things like that. And then there's more the HMI audio, which is warnings, which could fall under the safety island. And then there's like language model type implementations, which will lead to the need of an APU in the higher end system.
Yeah, audio, you can spin audio down to like its own domain, audio DSP, right? You've got all these different features like ESS, what's synthetic engine, synthetic sound synthesis or something.
Yeah.
You've got your,
There's that too. Yes.
and then you've got your internal, because if you have big cars, big SUVs or vans, you want speech.
Oh, the intercom system.
Yeah, I forget what it's called. There are obviously like short forms for this. I did look into this. I worked with my team to actually break these down a few years ago. I remember all of this, but there was like 5 or 6 different just use cases just within audio DSP workloads. And then you have how many channels of audio do you need? How many speakers do you have in your, so then you can do all of that with the DSP, which is on board, or you can even do it on CPU, or you have an external amplifier to do it, which is its own separate ECU.
Exactly.
Same with the number of microphones that you have, right? Localizing the person who spoke, who spoke where, from where.
Yeah, that's the intercom stuff that we were talking about.
And then there's
From my
dedicated.
experience, the mixing of audio is actually becoming more heavy than the audio itself. Right? You can play mixing and also
As in multiple streams of audio.
Radio is going on.
music and trying to play it with the engine sound in parallel. Then you try to cancel some of those.
Noise kills.
Yeah.
Road noise reduction.
And then playing 4 movies in parallel, you have 4 streams, but 4 parallel streams, which need to come from the SoC, then go to the Bluetooth controller for the earphones. Yeah, audio itself is big, but I think it's okay to keep being this level. Otherwise, I will be too much focused on audio.
Yeah.
Yeah, but it's, you know, because it'll have its own set, you know, just like video, you know, getting that
Yeah.
review camera up on the screen. And I get in my F-150 and I get one kind of chime, and then I can tell after the system wakes up, I get a different kind of chime. So,
Yeah, I mean, I guess, no, it's interesting too, because, audio can be have real-time requirements on it, right?
Yeah. It's also ASL in the newer systems. It's ASL B.
And what?
should we limit ourselves to IVI here, or should it be cockpit? So now you got all the cluster stuff.
Yes.
Oh, okay. Oh, what's the better word then? And
Cockpit or is
To
me,
The display is covered.
I
The
understand.
graphics is covered in the review.
But we'll do instrument
That's
cluster.
Yeah,
The reason I thought of it, I think, because you said functional safety, and I thought of the cluster.
Okay, we'll add instrument cluster as well.
Like boot up time and stuff.
This is why,
Cockpit has to be ASIL certified. IVI is probably QM, so it's more the leisure part, not the business part of autonomy, right?
Even audio though, I mean, again, I think it depends on who you talk to, but even just a basic audio system has a form of ASIL that's associated with it, because if you lose control of the volume for some reason, that causes a safety issue.
And ultrasonic sensitivity, so they need to be made sure that you're able to pass them through.
That's right.
And
Yeah,
reliably.
any warnings, any
Any warnings.
telltales. Yeah, telltales, yeah.
good. Well, if we think that's the full list, we can
Phone
go.
projection,
What's that?
phone projection.
That be under audio or?
CarPlay and
Yeah, CarPlay.
Absolutely, yeah. Phone, yes, sorry, actual. yeah.
phone integration.
Cell phone,
Yeah, what do you guys call it? CarPlay?
Yeah.
Android,
For the smartphone indication.
Smartphone.
integration.
That's not, that excludes just Bluetooth only or media only. What do you say?
Navigation, but navigation is.
Android is what we cover on Baidu's. But in the Bluetooth media.
You have rendering separate navigation rendering.
it's added,
navigation.
Yeah, I mean, I think the difference with this system, right, is that ADAS typically, I think you kind of get everything up and running and then like you're always, like it's sort of fully capable, and if someone activates the feature, then you're just going, but this is all very, whether someone runs navigation or doesn't run navigation,
Yeah,
it's, right, it's much more unpredictable what the workload would be.
yes.
It's also the most visible part of this.
So you want to make it snappy?
You want to snappy and not have like,
Yeah.
obviously you don't want bugs on your ADAS system, but you also don't want bugs. The customer may not know about those bugs.
But yeah, if you want to click on phone projection, you want it to come up right away, not 5 seconds later.
Right, good. So if someone thinks of something else, we'll come back here. We can go in two directions. In the time left, we can either go back towards some of these software topics but maybe given the discussion yesterday, do we want to try to carve out what we think, at least for the ADAS level?
Did we come up with a similar set for ADAS in terms of workload?
We didn't, I think we didn't do it that way, but I think if we take I think we can, but maybe we'll do it in the context of what would a quote default level 1 system be, level 2 plus. Maybe not even level, I don't know if level 1 is even right, just because that's kind of a solved problem.
You know, like we were talking about, I feel like for IVI, we've got a good set now. We don't have different levels within those sets. The way I tend to think about ADAS and automated driving is interfaces, sensor processing, perception, which is different than sensor processing, behavioral modeling, and then vehicle control and HMI.
Fusion also.
Sorry,
Fusion.
fusion, that would be in the sensor processing.
Fusion of and cockpit.
Yeah, I'm talking about camera with radar.
Yeah. So sensor fusion, we do that in the sensor processing. So it's like the conditioning of data for further downstream consumption.
So on that point, right, now, I think the way you described it is that you put like a box around the model bit, right?
Yeah.
Now that model, the complexity that model can handle can vary, right? You have a model that is capable of making certain decisions or detecting certain scenarios, certain things, or creating certain actions,
So
right?
let me give you a couple of
And that's what-
examples and see if that resonates. Okay, let's just take a simple blind spot detection system.
Yeah.
today. I've got one sensor per side of the car. It's a radar. It's not even vision.
Yeah.
And I'm gonna do sensor processing, which is detections. I'm gonna do perception in terms of what do those detections mean to me, i.e. is there somebody in my blind spot?
Yeah.
My behavioral modeling is, okay, based on that condition, do I turn the light on or off? And the HMI is actually turning, the actuator part of it. And then, okay, let's take a totally different one. Let's use automated park assist. That's using surround view plus radars plus ultrasonics. So now I got all my sensor processing, same thing. My perception is now,
Yeah.
where is the parking spot? My behavioral planning is what trajectory do I need to get into that spot? And then the HMI and vehicle control is how do I get the car to follow that trajectory that I want to do? So the model fits like a huge range of ADAS.
These are the building blocks of ADAS, what he's describing. So you can have the different functionality relies, or different use cases relies with that functional block.
Does it not resonate with you? Because I don't want to put forth a model that.
No, that I think what you described does resonate. I wouldn't say those are use cases. Depends on what granularity you want to look at.
No,
Those
but
use cases.
what he was describing right now is one use case. Let's
Correct.
take emergency braking.
Yes. Yeah.
In the emergency braking, you have a camera
Yeah.
that detects an object or radar or picks up an object. And again, you go through the same chain.
So question is, would you have the same workload that is capable of doing emergency braking, or or your model that is doing the path planning and automated driving, is it capable?
Yeah, Umer,
Is the same workload capable, is the same
yeah,
model
yeah.
capable of doing?
What I'm trying to say,
or is that a
these
separate
building
system?
blocks, okay, the load could be different. And that is what I'm saying, trim level 1, trim level 2, trim level 3, where you could be having different sensor set. The resolution could be different, number of sensors could be different, but you're going through the same signal processing chain. Okay, you could be having more software which is processing it, or you could be having NPU or AI which is playing a better role in the high-end system, which you don't have in the low-end system. But this is what we have to start somewhere. These building blocks give you the basic idea. Okay, what do I need? Then you can go to a granularity where you say, okay, now do I need a single SoC or do I need a double SoC? Depending upon the sensor set.
Yeah.
So theoretically now, you could take, whatever Stephen puts down as these feature level requirements, which to me is the alphabet soup of ADAS. Okay, what features constitute an example? I hate it, but level 1 system.
Yes.
What is an example of a level 2 set of features? And then you can create from that into that model. What do I need? Oh, I need an NPU because now I need to do perception on camera data. Okay, how many tops?
Right. So that I completely understand, and I think I'm on board with that. It's the part where you start with the sensor data. I think we need to abstract that out because I feel like, again, because it depends on. I'm trying to think about can we take it all the way from end to end? Is that easier or?
I think designing examples like that, and you're not going to cover every base, but I think that's the way to make sure that you don't miss something. And you can't just make a generic camera because if what you're saying, for example, if we have a feature list that is, you know what, I want to do low speed urban automated pilot.
Yeah.
Okay, that's a wide field of, I could get away with a wide field of view camera and a lower resolution.
Yeah.
As opposed to high speed,
Yeah.
where I'm going to need, in addition, I'm going to need a long range,
Yeah.
high resolution, narrow field. And that will put different requirements all the way through the processing chain. It changes your ISP
Yeah.
throughput. It changes your NPU tops. It changes the way that you have your behavioral model.
So I guess what I'm trying to think of is to get to that, even the discussion that we were having yesterday with Neil, right? Get to the graphics model, right? And have the ability to think about it from the workload point of view, right? My workload is processing data, right? And that could be, the input data could be 5 megapixel camera, 8 megapixel, 12 megapixel. And the result that I get from the answer that I get from my workload should tell me whether it's as a frames per second number, right?
Whether I can do that or
I
not.
do that resolution or not, or to meet a particular response time, what is the resolution I can operate at,
Yeah.
or speed that I can operate at, and those are the kind of inputs that would go. You understand? That's what my head is at, to try and abstract this out and let the output that comes out from the benchmark drive that.
But I think we need to come at it from both directions.
Yeah, that is what my approach is. You need to have morph box kind of approach, where you say, okay, these are the different modalities of sensor I can have. Then this is the next unit, that is the next unit. And each morph box has not one component. It has multiple components there. We say, okay, I pick this one or a combination of both. So that is why I like this idea, what he was saying. You create a kind of morph boxes, then you say the box 1, 2, 3, 4. These are the possibilities. Then you play with these combinations. As you say, you can have a higher SoC. Then you say, okay, what can I add from the morph box? Do I need a more camera, higher resolution camera, or do I need a radar? Or do I need a LiDAR? Who knows?
Yeah.
So I think that this approach could work in this case where you say, okay, now if I have this use case, are these components working for this use case, or do I need to add anything else? And then you have this granularity where you say, okay, this feature set can cover with this trim level, or do I need to add something else?
In the end, the tier ones of the OEMs want to be able to take those benchmarks and assess what's available on the market to see if it fits their needs. And from a from an SOC developer perspective,
Mhm.
I have to take everything end to end into account. And so when we do get requirements from tier one, I always start with the sensor.
Oh, yeah.
Have to.
No, we do, yeah.
Right, and because then I go through the SerDes analysis. Okay, how would I connect these up with the SerDes? Okay, how many C5 or D5 backends do I need on those SerDes to handle that? Oh, okay, that's my IO. Okay, how much bandwidth am I gonna take up just to write these camera images out of memory? And you just kind of work your way down the line and you find out where you're running out of gas.
Yeah.
And I think maybe in a point, right, we're not actually trying to design a system.
That's right. I was just.
We're really just trying to get meaningful numbers
Correct.
and maybe at least a couple, and then.
And yeah, and I know, Stephen, it's like I told you last night, right? I'm coming at it from my perspective and maybe driving things too far. But if you start there and then you say, okay, if we have a framework and we want to eliminate some things, you can do that. But if you need to go back and fill it in, at least your framework is going to support the broader.
So it sounds like we need like a harness, right, of some sort where we can tune or tweak the input channels.
Yeah.
How many channels? What is the data rate of those channels? They may be representing different types of data, camera, LiDAR.
I divided it up by types of cameras. Okay, DMS, that's a 5 megapixel RGB IR camera. Oh, narrow field, forward-looking cameras, 8 megapixel, up to 60 frames per second. And then you select, and then you're like, okay, what's my alphabet soup? Okay, which of these do I need? And you plug them in.
Right, and that part of that's an Excel exercise, right?
It very
Like,
much is. Yeah.
And that's kind of where we're at. I think we can all do that.
Yeah.
And I think for the benchmark, we want to get to, okay, and now let's have a workload that actually stresses a system or pre-silicon, do that. So I think, yeah, maybe to make it concrete, what we'll do is instead of do another slide, and just as an exercise, obviously we're not gonna get it all done in one go. Let me call it feature. Level. It's not really a definition, I'll call it reference.
Sorry, my apologies, guys. I'm from online. I have one question. Is it okay?
Yes, go ahead.
Yeah, yes, please. So basically, just a few thoughts actually, just to better understand this benchmarking, right? So what we have is that we have these standard HD cameras to 5 megapixels to 8 megapixels. That's how the camera is evolving. Do we have any such evolution requirements or any such thing, capability requirement from, let us say, radar? For example, today you have a standard radar, then you now have an imaging radar, but then that definition is really not set in stone, right? You can have a different number of transmitter channels depending upon, your capability from a solution point of view. But generally from an OEM or a tier one standpoint, is there a requirement that there is an equivalent resolution from the radar? Because radar resolution is very different, but just want to understand whether you have anything coming, from radar point of view, getting into the benchmark, the document.
That's a good question. I mean, in terms of radar data rates or channels, typically radar data could either be objects or could be point cloud, or all the way to, it could be raw data too.
Yeah, but in the current systems, I don't think so. We have anything which is raw data where we are processing in the central unit. So most of the time we are giving either the point cloud or the objects that is coming in. So that is why even if you have higher resolution, we are processing in the radar as a standalone unit and then feeding the objects data to the central unit.
But you could have either a CAN interface or Ethernet interface, and it could be 4-channel radar or a 32-channel radar, and then the number of points varies from a few
The
hundred.
interesting point was the resolution.
Yeah. So, sorry, I just want to follow up on that one. The reason I'm asking is that, let us say that we have one architecture today where the radar comes with like a complete, fully baked solution on the radar. The radar will basically give you the point cloud data. Generally, the data rate is very low. So then you don't have much to talk about from benchmarking point of view. But if you can actually process the radar the way you are processing the camera, where raw data from the images come to the SOC, then the raw data from the radar comes to the SOC, then you now have to think about a certain accelerator like a DSP or ASIC or something, one accelerator block for the radar, just the way you actually had an accelerated block for the vision. Okay. The next thing that we can also think about is that in future, just the way you are talking about AI ML inference for the vision, you can even think about AI ML inference for radar. Means that now there is no differentiation of the radar from a camera as far as the workload is concerned.
Agreed.
What I can say, what is happening, what is my understanding in that area is you're not making the AI only on the video or only on the radar data. You're trying to create a fusion and then try to run the AI on that combined data.
So the way I think of that is today when we feed a vision input feature map to a neural network, it's 3 planes of data, RG and B.
Yeah.
And if we were to take radar data and overlay it on that, be it lower resolution, I create another plane that is essentially a range plane. And then I train my neural network on that. And to me, that's the fusion. But that's still at the object level. So I'm sorry, I don't know who was making those comments online, but I would say as a first level, and I'm a firm believer that centralized radar processing will happen just because it alleviates a lot of problems out in the sensor and it's a system cost savings long run. But I think at the first level, we should assume we're getting an object list or a point cloud. Just to simplify things.
Yeah. And radar had its own pipeline. So you cannot say that, okay, you can give it low priority. So you have to give it a higher priority.
Exactly.
And you need a dedicated processing of that.
Yeah. But I do come back to the comment about the resolution. Are we going to put benchmarks on that? I mean, if you think about it, the resolution and the accuracy, and one of the big things that's happening in things like adaptive cruise control right now is that people want higher resolution and higher accuracy because they want the most comfortable adaptive cruise control. And that's kind of the race, as far as I know right now, for performance in that particular feature. But I don't know how to relate that to a benchmark, to be honest with you.
Well, since you're the one bringing a lot of this up, I'm gonna put you on the spot also because of the time. Let's try to quickly define, we're not gonna get probably to level 3 and level 4. Let's see if we can't just define basic level 2 as a starting point and maybe level 2 plus hands-free.
Should we call it a feature map?
We break down to safety versus comfort in level 2.
Let's just do everything we would want for level 2.
So
Safety and comfort.
now let's see if we all have the same goal.
Yeah, I realize it's gonna be a year-long discussion.
Level one is feet off, level 2 is hands off, level 3 is eyes off, and level 4 is mind off.
Right. No, I'm defining this as level 2 hands-on and level 2 plus is hands-free. Yeah. No, and that's because, and I'll tell you why, because I think that's like most systems now have lane centering plus adaptive cruise control.
So Tesla just put out their latest update to their FSD driving last week, and now you could take your hands off that steering wheel. But they do have DMS.
Right, on the newer model. They've actually had it out more than a week ago.
Really?
Maybe you just got it because.
Well, I don't have the car. I just had somebody I work with.
No, one of our VPs has it. He's had it now for a few weeks.
Okay.
It's it drives him to work every day. Yeah.
So,
But we're not trying to, I really, Tesla's its own beast, right? But they're not gonna use our benchmark. So.
okay.
But, yeah.
So you mean hands-on? I don't know how to interpret that.
That means the car is actually driving for you.
But your awareness level is that.
But so here's how I'm defining it.
Even if it is in the lane side.
Yeah, here's how I'm defining it. It's lane keeping, ACC, and AEB.
AB also takes care of reverse AB.
What's that?
Back.
Yeah, let me add that too, though.
Now, what about automated parking? That's an L2 feature.
It could be, right? Yeah.
And it's hands-free.
Hands-free, yeah, that's true.
You can't keep your hands on this.
But we would add automated parking. This is what you would buy in most, like, let's call it mid to high trim levels. You buy a car today.
Yeah.
It wasn't a Tesla. I'm just trying to think, there's blind spot, oh yeah, blind spot. Although that often comes from the radar itself, but let's add it. And rear cross traffic. You guys know these documents. Rear cross.
Backing.
I'm not sure. I don't think I've heard rear cross traffic. Was that RCTA?
That's from the blind spot radar. And look,
That's memory.
Wider.
it can look wider, so if you're backing out, it could detect something coming behind you. Paul, I think developed this 15 years ago, 20 years
I was
ago.
gonna say, that's my patent, actually.
You have a patent on it?
With Chrysler, yeah.
Okay.
We presented it to them and then I got an email, hey, let's patent this.
Yeah.
And of course, they get awarded the patent, but I guess.
Well, you have to be, otherwise it's
Yeah.
invalid if you're not listed as. Okay. Yeah, is this complete?
Alert,
What's that?
spelling. Traffic alert.
And what
Road
about,
sign? Oh, like road.
Oh, no, it's not much spelling.
Oh, thank you. Alert. I guess road,
Sign recognition.
road's the speed.
And speed, yes.
Traffic.
That's
Traffic, yeah, traffic sign.
traffic speed, I think so, it is only
Yeah, traffic
speed.
sign is the other one, right? The lights is different.
Oh, high beam.
Or high beam, automated high beam,
Is that an L2 thing?
I think so, it is
That's
that.
pretty common.
Yeah, I have in my both cars.
No, but is it L2 or is it like
Or is it related
It's
to
really
LTE?
ATES.
the automated beam pattern?
Yeah,
What
so
do you-
it goes high beam when nothing is coming,
Yeah. And
then it goes low beam automatically. If something is coming, or some red light is there.
Okay, yeah, that's a, yeah.
ADAS.
Well, in that case, automated winds, wipers are also ADAS then.
No, that is,
We detect when you-
No, because it's.
that is nothing to do with that. You have the other sensors.
But this high beam assist is not related to any of the ECUs.
No,
you know?
Correct. That's
It's
what-
a headlight ECU doing it.
This is a side product, I would say.
Yeah, then we might
Out of
need it.
camera.
Yeah, that's what I'm trying
Yeah,
to.
the problem is because that thing comes to the camera.
Yeah,
Some of the, yeah, I mean, because
Oh, okay.
it then means, okay, I now need to, number one, identify that, as to what kind of light.
yeah, so I
That's
feel,
part of the perception.
I feel
The
there is a,
camera is an ADAS camera or
Yeah.
is the camera?
Yeah, it's
No, no, it's
typically
a
that.
ADAS camera,
It's
top camera,
typically
windshield
the,
camera.
yeah.
so it is a ADAS feature, otherwise how can it know it is a normal light or it is that light?
Yeah, exactly.
How does it differentiate between the intensity? So it is a ADAS feature somehow,
Okay.
but I could not really say that, okay, it is SA2 or SAE1 level.
Yeah, see, it talks about automation level.
And
so it won't-
what about the blind spot detection? Does it come into level 2 or it is level 1?
It should be here.
I'm including it here anyway.
Level two.
So,
It's an ADAS feature, which is different than automated driving. It's driving assistance. It either gives you information or it reduces your workload as a driver.
The reason why I'm including it is also if we go back to these domains.
In that sense,
have it.
AED, not ADAS.
Emergency braking is ADAS.
AEB takes temporary control of the vehicle, so.
Yeah, however, this is not ADAS functionality.
No, it's level 1. It's level 1 automated driving.
I mean, that's a regulation point.
Now it is a regulation in 2029, but until now, it is an optional feature which OEMs are giving. There is no regulation in US.
In the US,
Yes.
Without AEB, it is not possible to get type approval, but without ADAS, it is possible to get up type approval.
Okay, I don't know about that.
but that's Japan and Europe. In the United States, ADB is not required.
Which means now, yeah, that's.
However, usually ADAS be not the safety feature.
Oh, you think ADAS doesn't mean safety feature? I think it It includes safety features in my opinion.
Including safety feature, but the AEB is completely safety feature.
Yeah,
Only safety.
And then,
this was where I was mentioning comfort versus safety.
Yeah.
The ACC is a comfort, AEB is a safety.
yeah,
Reverse AEB
Yes,
is
I'm
blind.
gonna say comfort plus safety. And the reason is, right, is because in a central compute, it would probably need to do both.
Yeah, yeah.
so then you need to add FCW, front collision warning.
Oh,
It is one step before AEB, yes.
Yeah.
Because that is what is happening. You are getting the red alert first, then it emergency brakes.
So would you then deploy these safety?
LDW.
So you said they'll be deployed in the same domain. Is that true? I mean, or would you, as a supplier, partition the system out to say these features which have safety requirements will run on the safety domain and not safety?
Simple way, the safety features will be always active and the features will be typically active when the user selects. And then you either pay more or you have a higher system.
No, I'm talking about like, that's from,
From
The
hardware
activation and-
perspective or from software perspective?
I'm talking about where both, right? I mean, I'm talking about the compute hardware and software perspective. That's what I'm talking about. Where would you partition the safety workloads to run on a part of the hardware, the compute hardware, which is safety certified, or a separate domain, which is running safety critical workloads, or is that not a?
It is not easy to do that way, especially because when you have only AEB or lane departure one, these are two features, right?
Yeah.
You get the inputs from radar camera and then you process it. And when user turns on ACC or lane keep assist, you need the same inputs plus the new inputs, if there is new inputs. Then now you cannot, if you keep the separate, then developing the system is difficult.
So you're talking about the pipeline, it's the
So-
same pipeline,
And
but you add an additional bolt on to it, right?
Yeah, even the comfort feature still adds on top to the safety. So AEB is braking, and then when you have ACC, it's also braking, but in a comfort way.
Yeah.
You don't sudden brake, but you slow down and slow advance. And then you rely this as the base mechanism, and then you add the feature on.
So maybe the priority can change how you prioritize some tasks, because if you say, I have to prioritize emergency braking over lane keep, so you prioritize AEB over the lane keeping.
Yeah, keep it
But they're not redundant. You can say, okay, I leave this part out and this part.
Now, if you bring that point, the safety levels, ACDB, right? It is not actually covered here. I mean, doesn't need to be covered, but if you see here, the ACL B versus D, it is applicable for something like that. The braking ECU is not our ECU. It needs to have a redundant path. It needs to brake. In AEB, it needs to brake if it detects. So there is two paths there. I mean, if the radar is detecting and showing it like we were talking. Should we cover safety ASIL levels also within this somehow? Because some systems ASILs are regulated versus comfort features are not regulated. ACC, I don't think if it's going to be regulated anytime in the next 5 years, right? It's just a comfort thing.
but for every system you deploy on a car, don't you have to go through an FMEDA?
Yeah,
assess?
but then it's ASIL B versus D impacts are different at the system level.
Okay,
Yeah.
okay.
The level defines how much you do. Yeah.
Great. We're actually at time for the session. Obviously, we should have
I like the sensor.
booked a lot more time.
I would
Something we
agree,
haven't
I would
used
agree.
today.
Okay. What we'll do is, I mean, we did, and maybe just, as reference, right? Going back to the very first technical report AVCC did, right? I was showing this yesterday. We kind of double check it against that. The goal was not to finalize, these topics today, I think we did. I think we identified some really good content. And then maybe just as a summary going forward in our benchmarking work at AVCC, I think what we'll end up doing is normally we meet every week. I think I get it on a cadence where like every other week we do pre-silicon benchmarking, and every other week we continue the path towards system benchmarking. And so what we can do is go back and then spend specific times on each of the sections. And then how this gets updated either back into either updating some technical report we've already done, or creating something new and then thinking about what would be the steps to actually make a real benchmark out of that as well. What we can leverage from what we're doing with ML Commons, because they're doing the AI perception part, and that's great. But maybe we want to use some of these discussions to help push back to some of what they're doing as well. The version 1.0 of that, I think is getting defined pretty well. But for example, the driver monitoring piece, maybe you start, for version 2.0, there might be some additional things. I know we want to get radar into that as well.
I think that's going to be a good segue for the next session, I think, because we're talking about foundational models, right? And that's again where the way I understand is where the ML Commons work comes in. It's more focused on the AI deployment testing and getting the inputs and all.
Right, exactly.
So it would be good to have some continuity from the first report and see how that kind of filters in, or what the roadmap is from either from that for that to feed into these subgroups, or for the subgroups to feed into that.
Right, no, exactly. And I think what we'll do as well is we can, in some of the discussions, work a little bit on what we want to define for the system level as well. Because obviously what we didn't cover was the software related topics. How much does the OS matter? But maybe that's not a priority. That might not be the driver. I think obviously in terms of SoC suppliers, getting some clear, targets early on is also helpful.
Who are the AI experts in the working group?
Well, Predrag actually knows quite a bit about that.
Because now we're going to start to come up against, okay, for this feature in this sensor set, we need, exactly. What model? We need to do detection. We need to do segmentation.
So that's where the work we're doing with ML Commons is completely focused on the AI. That's been most of the discussion.
There's already a list of models, no?
Yeah, there is actually a list.
I don't know. Okay, because from our side, I don't know. It doesn't look like Florian's on call.
Okay, but
Our guy in Munich.
I will let me forward that. That's a meeting that meets every Wednesday.
Okay.
So I'll forward that meeting invite to you guys.
That's the ML benchmark.
Yeah, right.
Yeah, it is. It's
Okay.
Florian normally is the one that's assigned.
Right, and that's the one where that really is going to carry that AI piece forward.
Okay.
So I think we don't have to do that, but that's why I kind of want to make sure we're not missing other pieces. It's like you got the perfect MPU, but you know what? We can't run any features.
No bandwidth available.
Oh, we forgot the optical monitoring camera, and now the ISP doesn't get it. Right? So Predrag, I hope you're online. Good, you are.
Yeah.
Are you able to share? Do you have permission to share?
Yeah, I will share my screen. I think for this session, for some reason camera's not coming up. We'll maybe do half of it more tutorial style, and then second half open it up for the style of discussion. So I will share my screen then. Okay, so I hope you guys all see this.
We do not see it. So.
Not yet. Okay, let me see. Let me try again. How about now?
No, I do not see it.
Huh. Okay, so let me try entire screen and let's see what happens. Do you see anything?
It doesn't even look like you're sharing for some reason.
Does he have a presenter slides?
Okay.
Oh, you don't have presenter rights. Let me see if I can get that to you.
Okay, that's different then.
Okay, now you should be able to share.
All right.
Nothing. Everything's coming.
Okay, came up. Okay. How many engineers does it take to? Yeah. Okay. So welcome to this session. We'll talk about the foundational models, mostly for safety and some for convenience. The motivation for this is that, of course, the AI, the models are really advancing very fast. In last 2 years, this has been, become very hot topic. Prior to that, bird's eye view models. The overall motivation is, of course, that with the supervised learning that requires bigger and bigger data sets and more and more edge cases, it's kind of hard to make both data sets and training very efficient. So the idea with foundation models is to get to tap into the knowledge that is in some ways contained in image and video captioning. And whether you want to call this HEI or AGI for the driving domain, it certainly does mean that you have some generalized knowledge that is in some data sets and that you would like to kind of incorporate. Some of the advancements as of 2 or 3 years back were, in 3 levels of generalization. One is kind of the bird's eye view models, the models of bird's eye view plus time, where multiplicity of cameras and in some cases LiDAR is incorporated over time, and then you have a little bit better situational awareness that you would have had to do previously with more late fusion. The second thing that happened is also the language-based models. So technically incorporating some of the captioning that you can see in some images and video, and incorporating that as yet another modality into VLMs or visual language models or multimodal language models, which just means that aside from cameras, you have LiDAR, radar, and other things, IR, and so forth. And lastly, the generalization that comes from self or weakly supervised visual foundation backbones, which are kind of not trained for multitask at the onset, but are trained to generally capture the low-level features and then can be used later for different tasks. As I mentioned, the data sets are getting much bigger and bigger, and I think the realization where you can't have models for just cone detection, but you need to look at it holistically, or other very specific models. To do more holistic approach, you do need to, as I said, tap into the knowledge that is containing in different data sets. I also want to emphasize here that, for the benchmarking, we, at least in the 004 recommendation where we did data sets and models, we didn't necessarily cover any of the safety models or any of the newer models that I just mentioned, the bird's eye view and VLMs. And that's kind of the motivation that, since it's been almost 2 years that we've published that we want to update those recommendations with the newer stuff. And there's an upcoming ISO 8800 recommendation that actually includes safety, but more for the vehicle AI, as opposed to looking at safety on the kind of FUSA level. So it's kind of timely to add some of these mechanisms that enhance safety. So just to give a little bit of nomenclature here, what has transpired is, multimodality, meaning multiple sensors early fused in bigger and bigger models, or you can do still older style late fusion with having separate models for different modalities. Fusing backbones, meaning you're having a bigger backbone that can be used for multiple tasks, therefore you're saving a little bit on loading. That is, for example, taking one image, but then splitting the heads into object detection, segmentation, key point detection, and so forth. Fusing task, meaning that in the kind of left to right flow of things going from, perception all the way to actuation, you can actually fuse some models and make them a little bit more accurate and maybe efficient. But on the other hand, now you have to figure out how to schedule these bigger or much bigger models onto your, MPUs, GPUs, and so forth. Diversity models just means that you have kind of mixture expert models, sometimes these more specialized safety models that are kind of adding to the mix and doing same type of detections, but doing it with a different style of model, if you will. And then lastly, as I mentioned, fusing text modality, which kind of is trying to tap into this general knowledge that's hopefully compressed in language. And again, when I say general, I don't mean like general intelligence. I mean general enough for driving specifically, not for all the physics and everything else that other domains would cover. And then the other thing is not just the general knowledge, but also the sequentiality of chain of thought, if you will, where you're not trying to do just one-shot inference, but in one or two or three inferences that are back to back, as if you're talking to like a LLM, right? It has history and it can actually refine the answer as you are probing it more and more with questions. So kind of the older view of things is if you look at different, and I call channels different specific usages of models for different purposes, and I will explain in a second. So primary channel is where most of the inference would happen, right, end to end. Redundant would be the one that's basically a copy of it, and you're basically using it for checks. Diversity would be, again, these models that do the same thing, but do it slightly different so that you can do checks between one model telling you one thing versus the other one telling you something else and then merging it later. Shadow channel just means some of these models that are not actively contributing to the actuation, but they're doing detection. So for example, you're checking whether your future model is actually how it's reacting. But being dormant in a sense that it's not actively doing anything to the actuation. Fallback channel is, of course, a fail-safe operation. So when the primary channel, when we detect a fault that is not recoverable, then we can go to the fallback. The upper shows really kind of the more classical view where you're doing, different sensors, different sensors with different models that are more specific to those sensors, and then you're doing kind of later 2D, 3D fusion, and then overall with multiplicity of 2D fusions and 3D fusion, you are, let's say, establishing this bird's eye view or a grid, if you will, or map, symbolic map, before you proceed to planning. The darker green boxes, these extra safety models that are either done classically with the infinite analysis or even with the mini nets, where you're checking the status of the sensors, whether they're still operational, and also the status of the outputs, whether they still have rational outputs or not. So, for example, checking whether the sensor is still on, whether it's maybe not polluted by dust or snow or some other things where input output of the model would not make sense given that the input is already not reliable. And then the output of the model would be, can it be checked with some simple checks to even have a rational output, right, where some things wouldn't make sense and you can check it pretty quickly. Now that can you know, the upper part is kind of what I shown on the previous slide, but the middle part is kind of what are we doing with bev-formers or birds of view transformers, which again can have both time and now text. So by adding text encoders, decoders, and by text I mean not necessarily that you are externally having to input text, but basically it has learned queries or canonical text that's useful for driving, such as can I go straight, can I go left, can I go right, those types of things that are relevant for driving and that are already embedded in the model itself. So by the dark black text, I mean internal, if you will, text that's not really input from the outside. That actually adds yet another block, if you will, in the birds of view transformers, which combined with the visual encoder can be cross-checked, and then you can see basically for example outliers, or for the you know, zero shot inferences. You can actually do some inferences even when your supervised part of the visual encoder may not have good reliability. The more kind of transparent part on the bottom is the externalized text to text, right? So this is kind of your not on a critical path, not on the ASIL path, which is kind of the lighter green. This is kind of your DC or digital cockpit type of interactions that the driver can actually engage with the system, but should not affect the system itself. In other words, whatever loading you have on the ADE should not be affected by the queries that are coming from the cockpit itself. Some challenges, I'm going to go faster to this, that everybody's aware of is basically getting to all the nines in terms of reliability, and whether you call them edge cases, outliers, anomalies, auto-distribution cases. That's really where a lot of problems occur. And they're kind of different in nature. Some are perceptually challenging, some are prediction planning challenging, and some are trajectory actuation challenging. So under perceptual, you know, you're dealing with different size of objects. Either they're too small, too big, either they're temporarily occluded or permanently occluded. You know, you can have different constellation of object that's unusual, crowding where, you know, for example, people or bicyclists are all together, so it's kind of hard to detect. Different classes look similar, but behave differently, and vice versa. And things that you haven't seen before, right? You haven't been supervised, trained on it. And again, there's an effect of influence of objects, right? Sometimes an object presence in a scene can actually help the object detection of the other object in a scene. So you're kind of given a better context to detect the object. But opposite can happen as well. A presence of an object in a scene can actually affect the detection of the other object negatively. And then on tracking prediction planning, so you have a temporal kind of aspect here is, you know, how do you infer the intent if you don't have any kinematic movement history, right? So you just saw the object or person, and now you have to figure out the intent, but you don't really have any frames before that to see any move, or they're not even moving, right? Figuring when you're doing supervised learning that you're not confusing causality and coincidence, right? So if the cars are starting on the green light, should you be starting or not? Because others are starting, or because you have a green light? You know, that type of dependency. And then all this multi-agent action reaction, what can, you know, possibly happen in the future versus what can probably happen. And then just kind of known rules, if you will, that are maybe not strict rules by the book, or some shortcuts that because of the safety, you would rather do a longer route which has right turns than the less protected left turn. And of course, in trajectory actuation, it's, what are you optimizing for? Are you optimizing for speed, for safety, for comfort, energy, efficiency? And again, what I was mentioning on the sampling, if you look at the right-hand side, you have two roughly types of problems. One is uncertainty due to really hard to see objects, if you will, hard to recognize. And then ones that are rare. You haven't seen them enough, right? So it's kind of slightly two different problems, if you will. On the errors themselves, how we are treating errors, of course, it's not as simple as just the MSE on the output of the network, right? What's your loss and square loss, right? It's also whether your and when you think of a system in the upper right, each model is down upstream from another set of models, right, for another task that's downstream, right? So how much are your errors at the beginning affecting the control at the very end, right? That's kind of one thing. And do they affect you, right, at all in the actuation, and with what's the gravity of the scene itself? Then temporal things like, if you do something at frame 1 and that is a small problem at the beginning, but becomes a big problem at the end, how do you account for those types of errors? Also internal errors, such as, models that have internal state, if you will, that have memory of internal state, and let's say there's an error there, how does it affect the next frame, right? Concurrency, meaning, sensors are not totally independent of each other, right? So any sensor that has, light or normal light input will be affected by similar conditions, outside conditions, right? So they're not totally correlated. And then sometimes you have, a sensor off, but let's say a model is taking most of these sensors together. How does it affect the rest of them? And basically, I'll go faster to this. What was the reaction to this is basically making these early fusion backbones so that you can do more robust detections, right? So you're covering the spectrum of different angles of the camera, time as well. Whatever in spectrum, I mean angles, if you will, rather than spectrum as in normal light versus IR, and then handling noise on one sensor and then compensating it on the other one. Shared backbones, as I mentioned before, that's where you're really making the backbones a little bit more generalized, and also saving on loading. Also, you could add outputs that are, just estimating the uncertainty of the model. And then now the transformers, this is where things get interesting, and that is, cross attention between different modalities or different sensors, right? Cross attention temporally, so you're looking at, current frames versus previous frames. And then all sorts of tricks that we're doing in visual transformers that are not necessarily present in the language transformers. Finally, we have the language-inspired transformers, which are using, and I'll get in a second what that means, is you're using either clip-style text encoder, or they are using kind of so-called adapters, where you're actually extending the tokens, visual tokens, with text tokens, or vice versa. Other usages of transformers are, aside from bird's eye view, is things that are not necessarily either visual or language per se, but companies have done their own tokens that help them identify lanes. Again, this is maybe not the latest, but 2 years back, they come with their own token vocabulary if they want to predict actually what is the layout of the intersection in terms of lanes, lines. If you don't have a map, you have to figure it out, or how the curves are going left, right, and also up and down. Also for motion prediction, so you're trying to predict the next token, if you will, that's also symbolic. It's not a visual token, it's not a text token, it's your own, basically either learned or explicitly given. And then aside from these discriminative tasks, there's these general ones where you're, and text ones where you're trying to, text ones in a sense of caption usage, we're trying to kind of figure out this common sense logic. So if a detector is seeing something on the billboard, is that important or not? Or seeing some mirror reflections of surfaces, or having people in different weird costumes, and you have to deal with that too. Bicycles on the back of the cars that are really not moving anywhere, right? So those are all examples of common knowledge, if you will, that is kind of hard to train. Or, I mean, once you know that the model is not performing, it's maybe not hard, but you still have to get the samples. But is kind of part of the common knowledge where you don't really need to have samples if you can get that common knowledge of the language models. Also, understanding a bunch of text on signs, like parking rules, like you can park here at some time of the day, some time of the week, and stuff like that. So that's where the language models can help you. That's kind of more convenience than safety necessarily, but it's still helpful. And then the interpretability of what the models are actually seeing and what they're intending to do. So the example on the lower left is from Lingo, I think from Wave, is what objects is it focusing on? And let's say it's focusing on a sign that's, I don't know, what sign is this for? I can really tell, but maybe left idle cannot do left turn, or a stop sign. And then on the right is kind of description of the scene, right? And it is, what is advisable not to do and what is advisable to do. And then on the lower right, it's really, if you're in fully automated driving in the AD L3 and 4, what is the model trying to do? Actually, what's its next intent? These are some foundations of how we got to the VLMs or MMLMs. As you probably already know, attention is all you need was kind of one of the first transformers that basically started the trend. It was like 7 years back. The second one is VIT, so visual transformer, that kind of took that concept and applied it to a two-dimensional space. The third one is CLIP, which is contrastive language image pre-training, which is kind of where things got interesting in a sense that you had this kind of the lower right part, where you had like a regular image encoder, which is, I think this is like a dog in the corner, and then image encoder of image encoding and embedding of it. And then the upper part was the for several different canonical sentences, potential sentences that have their own encoding, text encoding. You're trying to see a cross correlation between the two and see what matches what. So technically, if you find, and that correlation is learned, if you find a correlation between image vector and the text vector, and where is the highest correlation, then you can actually say, well, this is the text that matches the image itself. That's kind of the main. And this is really used a lot. The CLIP style is used a lot. The other one is I'll get to later is where you actually append both the text and the image tokens, if you will, and then you actually train a model like that. And again, Dino is one of those purely vision foundational backbones that basically are useful for many tasks, but were not trained initially for many tasks. They're just self-supervised trained. So what are these foundational model architectures? So we can split this based on tasks, based on modalities, and how it's combining these tokens. And what are the differences between visual transformers and LMs, right? So by discriminate, I mean mostly the detections, right? So you have some inputs, you have some internal canonical text that nobody's inputting, it was learned. And you're trying to do things such as either 2D object detection or bird's eye view or other things in prediction and planning. So basically, those are models that you would see as an evolution of the previous transformer models that were kind of doing more visual and symbolic. Generative would be the ones that are kind of more driver oriented, where you're trying to get a description of a scene, or you're asking about something about the scene, or you're asking about the advice what would be a good next action, planning. And then also there's generative in the sense that you could actually affect the planning by saying the style of driving you want to engage in, either aggressive, less aggressive. And then modalities already went through different sensors. Also temporal aspect of it. And as I mentioned, you can roughly split these VLMs or MMLMs into ones that have the encoder, decoder, two encoders, if you will, the language one and the visual one kind of separate and then later joined together. Or you can have ones that have these tokens, visual and text, together, and they'll learn together. I would like to highlight actually some differences here because people tend to kind of bundle everything under LLMs, and it's not the same thing as visual transformers, particularly because visual ones are, the tokens are really not a sequence. It's a representation of patches of images that are basically in 2D space. So you're not really using masking. You're not generating next patch. So there's no temporal aspect to it. Or the other thing is visual transformers are usually using different type of attention that is more aware of spatial things like patches or image as a pyramid or hierarchical pyramid, or so-called deformable attention, where you can actually scatter the points not in a 3x3 or 4x4 on convolution, but you can also in the attention actually pick and choose which tokens you want to pick from which positions. And it's more dominated pretty much by the number of tokens rather than the depth or the width of the tokens themselves. And then for LMs and LM encoders that they use in these models, they're really not good at localization because the labeling is not good at localization. So whenever you're looking at the image or video, you don't have the exact location of the object as to which pixel, right? With height, right? You're kind of generally describing things. So you will never have that level of locality, precise locality, as you can get from just the visual encoder. Also, the labeling doesn't go all the way to how much do you press the pedal, how much do you press the brake, and it's kind of more qualitative rather than quantitative. So there's some imprecision there. There's generality, but there's a little bit imprecision there. And of course, relative to LLMs, these LM encoders are much narrower in vocabulary, right? So you're dealing with much smaller subset of things that are describing driving, and you don't have any tolerance for hallucinations, and you want short answers and actionable answers, right? And very short time to the first token. So you don't need whole novels. You just need something that in few words can describe what to do or what it has seen. Therefore, it has much less loading than LLMs. And this is kind of the more detailed view. And I'm about to finish here.
I think I saw Ramesh, has his hand up for the question.
Yeah,
Okay.
yes, please. Sorry, very quick question, actually. I think, it's a very fascinating topic. One thing I would like to understand is that, so my understanding is, my understanding as a user of ChatGPT is that as a user, when I ask questions, like, it gives me wrong answers. I don't feel bad because nobody's dying, right? Generally, like, I get an answer and then, it gives me some wrong answer. I'm okay. There is always a human being who is actually there to sanitize the answer because there is a guy responsible. Now you're really talking about automated driving, right? Pretty much the driver is not there, or the driver is not doing the driving job. I'm trying to understand the ISO 26262 versus some of the other safety aspects. How do you actually incorporate those in these large language models?
How do you, well, you can't really incorporate it into 6262 because these are based on data sets and models. These are not based on basically code that you can inspect, right? Or hardware design that you can inspect. So basically, it's not trying. So the safety comes here from two things. One is first, the models are over parameterized. So basically, you don't have the same FUSA kind of things happening as you would with a CPU that has if then else logic, right? That's kind of one thing. The second thing is you do have a lot of redundancy here as well, not just in the model, but also between the models themselves. So and again, the third thing that you may be asking is you're comparing models that are non-physical world-based versus physical world-based models, right? So when you look at your chat GPTs and what it was trained on, a lot of it is basically not good information, right? Because you can't really sanitize it. You would need an army of labelers just to go through that, right? With the automotive models, things are more constrained in a sense of first what you're describing and how it's being described, right? So there's a lot of it can be inferred from the physics of the situation, right? But then secondly, even for the captioning that's coming from the users, there's much less opinions and much more describing what's really happening, right? So now you're still going to have the the danger of hallucination to some extent, but much lesser extent than you would have with the kind of socially driven or internet driven learning, right? So the driving is much more, as I said, physical world and physics world kind of oriented. So there's less of the kind of noise, if you will, that you get, training noise or labeling that you get in these other fields. That's kind of the best answer I can give you. Again, the 8800 is going to address these, ISO 8800 is going to address some of these sort of questions as to why is this different than 26062, right? Because you're dealing with a slightly different setup.
Got it. Yeah, actually, thank you so much for this response. Really appreciate it. Maybe one minor question, actually, that so my understanding is that you need various types of sensors, right? Because it's not just the vision. You also need something like, for example, the way I look at the driving is that the driving is actually a full body experience, right? It's not a vision only. Like when you sit in the car, right? Your lower back is telling you how bad the road is really, right? Now, when you touch your steering wheel, it is really telling you whether you are inflated or the tires are properly done. And then you don't see the ambulance, right? You hear the ambulance. So it is really like something like the whole some people are really kind of putting all the eggs on the vision basket. I'm trying to understand whether there is a better way to think about this automated driving. Like, for example, you have those other sensors coming into picture, providing their own inputs.
Well, you can do a lot with vision itself. You do need a little bit audio as well, because the external audio, I'm not talking cockpit stuff, I'm talking external detection, right? So you need to be able to, if you can't see the emergency vehicle, you should be able to hear it and roughly know where it's coming from, right? So you can move to the right side. The other sensors are still there. So your seat sensor is basically your IMU, right? Your localization is, you have GPS, you have IMU that actually are helping you with the localization. The cameras have done a good job in conjunction with these bird's eye view models, right? So previously you had multiplicity, this is like several slides back, right? You had multiplicity of different models that you had to hand fuse, writing code that will actually do mapping between many cameras into one, as we call it, bird's eye view or top view, right? Symbolic view of things, right? Nowadays, you can do that pretty much automatically because you're training it. So you're taking many cameras at once. You're taking history of those cameras, and then you're composing an entire picture, like as if you're looking from the top. So technically, a lot of stuff that maybe previously was done with the LiDAR maybe doesn't have to be. You still have the problem with conditions, weather conditions, like, at some point, if you want to see in the dark, you still have to have a better camera, or IR camera, right? But it's still cheaper than the LiDAR. And some other cases, you can compensate by doing maybe not the cheapest radar, but the 4D imaging radar, where you can actually see through things that visually you wouldn't, right? Including the LiDAR, because LiDAR is also visual, right? Maybe not the same band as our eyes, but it's still visual. These models actually take both vision and can also use LiDAR and even 4D radar as an input, right? So they're kind of agnostic. I think the more emphasis is on vision because it's cheaper, like 6 cameras, that's typical to these setups. It's still relatively cheap relative to LiDAR or imaging radar, right? So it's really kind of software driven or model driven, because there's really no software here. It's mostly models, bigger and bigger models, right? And this is where I tried to, this was kind of the last slide that I wanted to show, and maybe that will answer a little bit of what you're asking, is if you look at the AD and ADAS, right? I just kind of put together some things that are both in terms of spanning different tasks, but also spanning different features. So typically you would, for AD, like L3, L4, you would have end-to-end, either a big end-to-end model, which is not that typical yet. Some actually companies are trying to do that, or a piecemeal end-to-end. In other words, you have several neural networks that are kind of feeding each other one after another. So it's still end-to-end, it's just not one humongous model. And then for ADAS, it's kind of, again, this gray area of low L2, L2 minus to all the way to L2 plus plus, and the capabilities of, a huge range of things, right? Where L2 minus gives you mostly some level of perception, maybe not that much actuation, to, at L2 plus plus, you're getting, a lot of actuation, if you will. So it's kind of hard to bond it as one, very crisp block. But if you look at perception, prediction, planning, actuation as main phases, if you will, autonomous driving, different models will stretch or span different of these tasks. So bird's eye view models are mostly for perception, including some short-term prediction, for example. So it's both tracking and, a little bit of prediction into the future. That can involve, as I said, both the camera, cameras rather, as well as sometimes they use one LiDAR, but they usually don't use like more than one LiDAR. That's kind of most of it, mostly frontal. And then VLMs, which actually, as I mentioned, add this another component of basically understanding the scene in a sense of matching it with a caption that you've seen before, and then trying to inform you basically whether your detection is kind of matching the visual or not. And then what these world models are is really kind of extension of VLMs or MMLMs, multimodal LMs, where they may add some special encodings or tokens inside that are kind of memory tokens that are kind of helping you with the history of things. So you're kind of maintaining more or less a symbolic history of what has happened, if you will, the symbolic map of things, so you can predict better. But it's a continuum. It's not like, these are totally different things. They're so related to each other that, this is kind of just a tentative scale, if you will, where bird's eye view, VLMs, and world models kind of sit there. But yeah, they do combine all these sensors. I would say all the sensors. If you just look at individual models, you may see some differences. For example, Beformer uses both the cameras and IMU so that it can actually match the movement, if you will, the ego movement, and actually match the previous images, if you will, to the new ones. Bev Fusion uses cameras and LiDAR. You have what's called CRF net, which is combination of radar and camera, one radar, one camera. So you have a lot of combinations. The things that we don't see yet is, I don't know, at least not public in terms of models, is, I don't know, ultrasonics incorporated. That I almost never seen. Or some incorporation of audio into kind of a bigger model. You rarely see that. Just the focus of attention, since we're talking about attention and transformers, is not that much on those modalities. Anyway, this was kind of the last slide in terms of architecture. This is kind of a list of models, but I want to leave some time to really discuss about, the workloads and types of models. The ones that I liked, I'll just go briefly through them, is like this HiLMD, which actually uses both the kind of low resolution vision, if you will, over frames, to actually start paying attention towards very small or distant or risk or interesting objects that otherwise would have been missed, or there would be so much loading if you did it in high resolution. So this is kind of a very safety-oriented module that's kind of balancing both the, the performance and loading. That's kind of one example here. There's another one here that's also has risk labeling, meaning that the data set itself actually marks objects that of high risk, either because they're moving in a certain way, or you need to pay attention to them. So as I said previously, if you need to look at a pedestrian that's far away, maybe not moving, but you still need to look at it. And let me at least cover one more. And like Drive LM, which actually uses internal queries. So this is not necessarily a language model, but is inspired by the, how would I say, mechanics of the transformers and language models, in terms of almost having an internal language between the modules. And one module is perception, the other one prediction, the other one planning, but they're passing to each other queries as if you were passing your own queries to like ChatGPT, where you ask about something, it gives you an answer, but then you want a more detailed answer about a related thing and so forth. So there's a kind of iterative, if you will, querying here. And lastly, I'll finish with this one. It's one that actually also uses internal queries, if you will, that are not text, that are not visual per se, but learned, where it's actually communicating between the different modules, if you will, that are specialized. Like one is TrackFormer, which is kind of mapping, tracking agents or vehicles rather, MapFormer, which is actually establishing a map on the fly, so it's not coming from external sources, and then kind of merging those two. So these are kind of not the language models per se, but are language inspired models. So anyway, that's I'll finish with this because we've gone too long on the presentation side. Going back to the workloads and types of models, what do you guys see as interesting workloads or interesting models that I have maybe missed? Again, in this picture, in the lighter green, I'm covering mostly the AD and ADAS, so basically the business side of things, and then the digital copy would be things that are interactive, meaning that the driver can either instruct the AD to either go faster or slower or more aggressive or less aggressive, that type of thing. So changing the style of driving, you can see in this block here. I don't know if you can see my mouse, but basically changing this that will affect things. Or this informative question answering, right? So I think we were talking about yesterday, whether you're making a driver comfortable by showing it what the car sees in a sense of, caricature of the surrounding, let's say, what cars or trucks or pedestrians sees in the surrounding and makes the driver more comfortable. Or asking things. So if you're not in automated driving, so let's say in the bottom part where it's gray, you're doing your own driving, but you still want to have some ADAS capability where you're asking for, or it's giving automatically suggestions as to, can I move to the right lane or not, right, or left lane? Those types of decisions that are maybe common knowledge in case, there's a car on the right.
Kind of like you have another a passenger in the car.
Navigator.
Yeah, exactly.
Sorry, I want to ask you one thing, okay? So I've seen something, or what I perceive is that you're watching through your cameras a scene, a driving scene. And using the foundation models, you try to interpret that scene and you say, this is how I'm going to react in this scene. So you understand you're getting the visual to textual form. Just like I'm driving center lane, there's a car passing on the left and right hand side, and I give the indicator now to turn right.
Yeah.
With the, you can say, language model, it should say, hey, it is not safe to go to the lane because there is a car coming from behind, which is at 100 miles per hour. You cannot, but you perceive it due to the camera. So something like that assisted in the foundation models.
Yeah, so this is an example model. It's not necessarily my favorite here, but it's kind of along the side of your question. So you have either multiplicity of frames as a sequence from one camera, or you have multiple cameras as a surround, or a combination of, and then this becomes a matrix, these frames up here. So you are actually getting two things. One thing is actionable. The other one is more descriptive that you cannot really use as action. It's more for your own sense of comfort, right? So you can see at the bottom, the language model still has to transform or learn commands to give a actionable output. So if you're thinking ChatGPT doesn't help you because it doesn't tell you necessarily this command, meaning steering angle this, pedal this much, right? It doesn't give you that level of driving authority, if you will, to be used. So most of these models do have to have additional extra training for actions themselves. So most of these models, as I kind of tried to depict it here where, okay, they're more on the perception, prediction, planning. But if you want to get to actuation, here you have to do a little bit more additional work, because to get to actuation as to, as I said, steering angle and braking and pedal, you actually have to train them. You can't train them with qualitative stuff such as I press the pedal more, right? What does that mean? Or I move the steering wheel a little bit more to the left. What does that mean, right? So the labeling is not there yet for the actuation, precise actuation, if you will. So it will help you with prediction and planning. So it will actually warn you here, hey, don't go to the left lane or right lane because there's a car going 100 miles an hour passing you, or is going to pass you. So it will give you those warnings. But when it comes to commands as to being assistive in terms of control and actuation, you actually have to have good labeling set that has those or is reconstructed by other means, and then you can actually do literal actuation all the way end to end. This is why I have the some of these lines a little bit grayed out, just to emphasize that not all the models go all the way to the actuation. They kind of stop at trajectory planning, and because it's easier to do qualitative stuff there. But if you need to do quantitative in a sense of very precise angles, very precise commands, then you either need to leave it to either older style MPC type of thing, or you actually have to train that section to be much more precise about it.
So Frederick, maybe I have a comment and then a question. I mean, I think one thing with the foundation models that's interesting is for the older convolutional neural networks, right? You for, let's say, detection or perception, you get pretty good performance, and then it plateaus, and you kind of have this like asymptotic increase, but you'll never see every corner case. And the way I always like to, I said this before, but I'll just repeat it, is, if you have a 1 megapixel camera, and just to make it simple, each pixel could have 10 different values. How many different unique images could you create from a 1 megapixel camera? It's 10 to the 1 million, right? There's 10 to the 80 protons in the universe. So 10 to the 1 million is a very big number. Most of it aren't images, but your AI doesn't necessarily know that. So the point is, you never see the same thing twice, ever. So I mean, let me just finish a little bit. But it seems like with some of the foundation models, it has a way of bringing in additional information or reasoning information that lets you handle these corner cases that aren't really, we call them corner cases, but there's enough of them that there's, they're corner, right? So,
or cases that are not covered by the training data set.
The training data set is maybe that's the more explicit way, right?
No, that's a good point. In a sense that, I don't need to understand, like for object detection. So we're here having a combination of, let's say, classical object detectors and bearformers with the language, right? So what I'm asking, let's say internally in the model, I'm asking, is this an obstacle for me or not? Not whether, is this some animal that I cannot recognize, and therefore I'm going to ignore it, but I can't really ignore it because it's an obstacle. So with the zero-shot learning, or what you implied as a corner case that can be still inferred on, you can still ask a question, is this an obstacle in front of me, right? So you don't necessarily have to recognize this is an animal of a certain kind or a person, or, you don't necessarily need to identify an object.
You have to classify.
You just need to, from language, give a qualitative kind of answer as to, is this dangerous or not dangerous? Is this an obstacle or not obstacle? Because all these, let's say, animals or persons or whatever is in front of you share some small vector embedding between each other that actually speaks to whether it's, in this case, obstacle to me or not, right? So in that sense, it's able to help you qualitatively with things that you would call common sense, right? To lack of a better word, right? So it won't give you precisely, okay, the distance to the object is, this many millimeters, or this is a breed of a certain animal, because you don't really care about that. What you care is, for driving purposes, is, can I go there or not go there? Do I need to stop? So in that sense, it helps that.
And maybe to follow up on that. So for the perception part, the other thing is Bart made a comment today that kind of struck me. He said, as one of the presentations this morning, like, he's like, really maybe it's the prediction and the planning part that's really the hard, or the part that will require all the compute. And so that also made me realize, oh yeah, like maybe the problem isn't knowing whether you have free space, it's knowing whether it will still be free in a second. And that prediction,
Yeah.
again, but maybe hold on one second. I know that end-to-end AI, I mean, the older models, right, was like, AI for perception, and then the prediction and planning was all just traditional. Then I think Tesla said, yeah, we threw away hundreds of million, whatever, thousands of lines of code, and now it's all end-to-end AI. I had a demo at CES in a car. They're like, yeah, it's all AI. And it drove us, and it was pretty good. It felt a little aggressive as a driver. And then they're like, yeah, but it was all trained in Italy. It's at least a good excuse for why. It made sense. But what I want to get to so now let me bring it back to AVCC benchmarks. If end-to-end AI really, and maybe also with foundation models is the future here for whether it's high, let's say very, very good level 2 hands-on navigate on autopilot. So let's call it FSD, like Tesla FSD level, up to level 3 or level 4. If that's the future, then maybe we need to define our benchmarks with that, because like it's now that we're trying to define the silicon for those future systems. And so maybe to that point, Frederick, I mean, obviously we would pull this into the ML comments thing, but it might be interesting to figure out if there's one of these models and data sets part of it that would best be, let's jump ahead to the next architecture almost and find that benchmark.
How big are these models? I mean, the VLM model, like how many parameters do you have, or tops?
So this ranges, keep in mind that we have mostly access to the public ones, right? The private ones are closely guarded. But, because these things span not just perception, but also prediction and a little bit planning as well. So this is the Stevens ask, this also can help you with prediction, right? Because you're either having this qualitative advice as to what would other drivers do, right? Instead of doing some kinematic projections, you can actually, pretty much predict even the lines and how they are positioned and stuff. You can do a little bit of prediction as well, and planning from, the models that I've shown just a second ago. So these models are first bigger because they're trying to do a couple of things at once, jointly. And then they're much heavier because a lot of them most of them are really transformers. And as you know, the transformers are not easy on any of these accelerators, right? Yeah. So this can easily get to, 50, 100 stops, easily one model, right? And basically, that's where a little bit of a problem is for ADAS, is where do your tops, numbers stop, right? If you look at, how much silicon you want to dedicate to this and what the capability you want to cover. A lot of these things are mostly kind of getting into, what the latency for these things is going to be and stuff. A lot of papers really don't even mention the latency. They mention the accuracy, but not the latency. And of course, if you want to put it on real silicon, you care about the latency. So this is where for ADAS, we need to be careful as to not really go into these full-blown like world models, but actually go to simpler, slightly simpler in a sense of how much it does. VLMs that maybe don't do 3D object detection, maybe 2 object detection with language, or if we find a lighter model that's 3D plus not too heavy on the. So yeah, for ADAS, it's because the prediction and planning is kind of not as strong as on the L3 and L4. We would need to actually dial down which models we would include in the benchmarking. But for the KPIs, it would be a combination of not just, classical object detection, segmentation type thing, but also some of the prediction KPIs. How much were you off, going from A to B? How much were you off in the trajectories, like a mean thing? And then it's kind of a little bit tricky. I went too fast on that slide, but, how do you evaluate any of the, other things that are kind of more qualitative in a sense of don't go there, go there, right? It's like a binary thing, but you have to make errors a little bit. The loss function is a little bit more complicated than what you get from classification, object detection, where everything is kind of known for years now. So KPIs are also a little trickier here because you're trying to do, many things at once and kind of both left to right and both in terms of that and outputs, if you will.
I think, so Stephen, you were trying to touch upon this, and I think that resonates with me. Is like, we had this kind of convolutional neural networks, right? That was the thing. You had planning, perception, actuation, and all of that. Now we're seeing a move towards transformers-based models. Is that the right place to, start looking at benchmarking, or do we need to look a bit further ahead to see what's coming next? And maybe did I get that correct?
I mean, so really what I mean is end-to-end AI, meaning from sensor to, I guess, planning or motion planning or something like that. Or control even. If that's really what we're finding in our cars in 5 years, if Tesla's doing it now, right? Then that should be our model. Right now we're building up, our MVP with ML Automotive was ResNet. That was a great thing to set up a framework and get data. And we're adding better, I guess, we're picking up some of these models. I just don't know enough about it to say maybe there's a different model or data set you should focus on, and just like, if that's where we're going to go, then let's not spend 6 months kind of recreating the benchmark of what is getting launched this year, next year, because that's already, it's just.
If you look at the companies on the left, that will tell you what's already there, right? Not the academic papers on the right, but on the left, which of these companies are already doing these types of things.
I was going to say that the benchmark right now is more of a piecemeal, which is what Frederick was mentioning.
Yeah,
good.
And that's fine, because I think the focus there was around the setup, right? How do you automating the environment to set up your model, the data set, and then you can swap out whatever model you have running inside, right?
Right.
Ideally, you should be able to.
Right, you need it. Exactly. You need the framework.
The harness.
To use.
Yeah.
That's otherwise no one can use it.
Correct.
But maybe in terms of the.
So I'll tell you.
I think Paul still has a question.
If Tesla is the only one doing it, I made the point that there's not good labeled data sets yet. How do we create a benchmark about something that essentially we don't understand?
Right. Tesla has the data. That's their superpower, right?
Yeah, exactly. We're not going to give it to them.
They solved that problem in a immensely powerful way, but
I don't think
data
with foundational models, that's the input data set is not the limiting factor. I think that's
it's not
one of the main advantages, right? It's designed in a way that it can cope, and it's not limited by the training data set that you provide. It can react to better to stimulus that's outside.
Foundational models, what do you?
It's the end-to-end models, right, where you don't have, so, again, correct me if I'm wrong, but my understanding of this is we have this terminology called AB 1.0 versus AB 2.0, right, where you had your sensor fusion, perception, planning, control, and actuation. This was the autonomous drive pipeline, and each of them were their own stages, which had their own, may have their own models running or may not have any models. So so that's the traditional convolutional network-based automated driving, autonomous driving. Now what's happening is you have a single model where you just feed in raw sensor data.
Yep.
And that does.
Let's be a little bit careful here. It doesn't necessarily have to be end-to-end, right? This can be only object detection that has the embedded language encoded inside. So you don't necessarily have to go, full spectrum, from perception all the way to actuation. Like here, for example, I'm showing here is mostly in the perceptual part, and you're mostly doing, let's say, object detection with some language model, right, to double check things. So it doesn't necessarily have to be end-to-end. And to be perfectly honest, these BEV-formers, the initial part of the BEV-former is actually a convolutional network, right? So we haven't really thrown the convolutional stuff away. It's just that it's used at the bottom or the very left-hand side of the model itself. So just wanted to kind of
I think one other clarification for end-to-end AI doesn't necessarily mean it's only one model. It could be you have the perception model and the planning model, but you're using AI on both pieces of it. That's a little bit more tractable, right? Now you're just having to run both if you can do that. But you're to your point, having the data set to train either set of it is.
My understanding is a little bit different. So I can say that the training data set and then how you ascertain the quality. Because you can have a training data set where you say, okay, you're limited, but that quality of training is that high. You say, okay, if I'm facing something unknown or which is not of my training or untrained data set, then still I'm able to detect it with a high quality. So this is where we want to reach with these foundation models or AI models, is that you do not need to know everything from your training. But to perceive or to decode in the way that you say, yeah, I have very high confidence that what I'm detecting with my intelligence is the customer.
But what would
I think that's where we would actually have to change a little bit the KPIs as to how we are measuring the loss or the error, right? Exactly to what you described now. So for the zero shot inference, right? So for the things that I totally missed with the regular object detector, so I'm getting zeros there or full error, I can still ask an internal question, so to speak, is there an obstacle here or not? If it's true, then it's actually a good thing, right? You're basically getting a pass there. So we would actually have to change a little bit how the KPIs are done here, because now you're not asking a direct question as to, is this a certain animal or not? You're asking a question of a related kind, and therefore how you are measuring the MSI or mean square error or the log has to slightly change. So yeah, and it can be done on a very, very crisp model, meaning like object detection model that has language. So it doesn't necessarily have to even get into complications with prediction and planning.
I was just going to say, but if we need to be careful, we're going to shift the emphasis of how the data is used, how the benchmark data is used, because it's different for me to give you a network and the parameters and say, how fast can you run this on your SOC or design an SOC to, here's some input data, and I want to see how well it drives on the outside. Now it's no longer a device performance issue. It's a design issue. Get it?
Well, I mean, there's a performance issue too, right?
Data, how well do you drive?
Well, it could
No,
be,
that would be the,
different than saying, how fast can you run this network that I as a designer
Correct.
plan?
yeah. So that's, I think that, yeah, so you're saying how good is this the performance of the model in terms of how well it detects? Or is it the performance of the model? How
And it's no
quickly
longer,
does it run?
it's no longer a benchmark.
Yeah.
It's a design challenge.
And even when you, the second case that you spoke about, right, here's the input data, right? If your input data is fixed, you can train your benchmark or run your benchmark, again, it comes down to the same gaming of the benchmark, right? Because you could.
Yeah,
you
we
could
want to
train,
avoid the gaming,
correct.
and I think we're doing that by defining the entire set of workloads that goes into it. So that you can't tune one thing down and tune
Yeah.
something up, so that your numbers look good just for this benchmark. But does it make sense what I'm
but
saying?
I mean, I think it would be the model with the weights, right? And then
Yep.
you would
Yeah.
run the data set and, you know, you would have I guess an output trajectory or something might be the KPI.
But we don't have the model and we don't have the weights.
Well, that's why I was asking
Well,
what was available, you know?
So, and then it comes down to a model, right? What are you really benchmarking within a model? Because at the end of the day, a model is made up of operators, right? And it's some combination of those operators that's going to define how well it performs. Because that's the end of it, is the operator that runs, right? And you may have a model which has loads of transformers which will run really slow as of now, or something which has fewer transformers which and have acceleration on your NPU for those operators. So
Yeah.
That's my view, and it's a very, very like broken down view and simplistic view of it, but I think that's what we want to be able to get to, right?
And I guess
Here's a
that's
distribution of
secret sauce anyhow.
Sorry?
Well,
We're
if
not gonna
it's
get anybody's secret sauce.
right, it would be like a perfectly trained model if it was an academic, I mean, that's where these
If
academic
it's
papers.
representative enough is what.
Exactly right, meaning it's transformer-based model, so maybe the MPU has to run differently or the memory interface is different on these.
It's at the end of the day, everyone's.
So this
model
is no
gonna be
different.
It's gonna be,
Sorry. I was about to say, this is no different than what we are doing with the beformers, right? We do not have access to a private model that's kind of on the left-hand side of things, right? We have a public model that has its own Git, it has its own weights or trained weights, and we go from there, right? So it's not that much different with these models. These are trained models, these are public models. They're not, you know, super optimized as you would if you had gazillion dollars to spend on just one model, right? So it's not that much different from what we are currently doing, at least with these more modern models that we're doing in MLC.
so
As
let
I
me
said,
ask you, so these models, right, they're mostly focused on the large language. There's a
I
large
will
language.
say large language, it's language. Large language means something else.
Yeah, sorry. Yeah, it's language-based model or multimodal. I'm thinking of, so one of the use cases, one open source reference example that my team is currently looking into is this thing called Open Pilot. Pedrak, have you heard of it?
I heard of it. Yep.
Yeah, so it's basically it's what they call it an end-to-end model, and they just feed it camera data. There's no other sensors. It's just
one camera. Yep.
two cameras, front-facing cameras, and that's it. And uses
Okay, yeah, I meant one external camera, not. Yeah, you're right.
Yeah, and so maybe that's a good starting point, right? Again, because you have to start somewhere. We won't be able to cover all these different scenarios, and it's got a distribution of the operators that it has within the model, and we can get the performance data of how well that performs. It's Onyx based.
So maybe the question is, do our benchmark have all the operators that we think are
Yeah,
needed, right?
that's
That's sort of a way of asking the question.
So how well do these different operators perform? And that's
So
benchmark. Maybe that's too simplistic.
OpenPilot is not using foundation models, from what I understand. They use one camera, so it's not even a bird's eye view model. It has temporal information, so it's a little bit different model than what we're describing here, or what we're doing with bird's eye view and VLMs, right? So you would argue, I mean, other companies could argue, well, you're using this, public, relatively public model, even though it's a company that's behind it, that doesn't really maybe have the relationship to some of the models that these companies on the left-hand side of this slide might be using, right? So I think that's where you get into how relevant it is relative to where maybe the trending is going with particularly on the L3 and L4. Now with the Open Pilot, you are still at L2, maybe even L2 plus.
Yeah. Yeah.
We have about less than 10 minutes left. I had one other thing I wanted to ask about, Predrag. If you want to go back to the scene where you were showing the shadow, what was it? Shadow fallback.
First one.
Oh, at the very beginning?
Yeah, the very beginning.
Okay. This one?
Here we go. Yeah, and maybe just sort of the question, you don't have to answer it now, but redundant channel sounds like you need whatever you need for your primary channel. You better just double the resources. I think that's what that means. The diversity channel, the real question is there more than resources that we need for these other channels that somehow need to get captured in some way? So shadow, I would understand you're just going to run pieces of your model maybe to test it out. It doesn't have to be the full thing. Diversity, I'll ask you to explain in a second, Predrag, and also fallback. Like, what would be the sort of
and are they all running simultaneously in a car, for example?
Right, and on the same silicon. If it's on different silicon, then you can kind of.
If they are using AI-related technology, if it's more of a classical.
Correct.
Yeah, so let me go one by one here. So redundant channel, if you're doing, ASLD type stuff, and you're basically having a copy of the first channel or the primary channel, right? So it's like ×2 pretty much, right? So you're sharing the cameras and LiDAR and radar stream, but you are actually just doing the same thing. So that's pretty clear that it's like ×2. The diversity channel is doing things such as, let's say I have object detector of one kind, but then I also have an object detector of a slightly different kind. They're still trying to detect, they were still working on the same input output, but you're trying to see if you can identify some outliers, in a sense that you detected it on one, but you detected something else on the other one. So therefore, even though one object detector has high confidence, the other one has high confidence on something else, and they were trained on the same data, just a different model. And then you can actually get into rationality checks. So it's not going to be a copy of the first channel in any way. You may actually just pick some models that you are not too, how do I say, confident about, and then pick those. So it wouldn't be a duplicate